Now, good day, everyone. Good morning, afternoon, depending on where you are. Welcome to this session, and happy you're here. I would like to today to work on further customizations to the Go runtime and continue the work that we started last time. So, for context, last time we were working on this issue. And then we created some work in the Go runtime to answer that issue. And then after a session, we concluded by writing up a prose explanation as an RFC of what we were able to achieve with this inside CockroachDB. Now, many things have happened since last time. One thing that happened is that there were a few reviews on that RFC already. So if you head to GitHub and you look at the RFC PRs, and you will see that there were a couple of comments from different people already, and then the RFC was updated to reflect on these comments. And the main comments that needed to be addressed is that number one, for CPU usage, we can use a pprof directed approach as an alternative. I personally think that is not powerful enough for the needs we have, but it needed to be discussed as a possible alternative. Then we need also to compare the approach to manual instrumentation in the Go application code, CockroachDB code in this case. There were people pointing out that the scheduler ticks, which we focused on last time, are not a good measure of CPU utilization because the duration of a tick is variable. And so depending on what a Go routine does, they will use tick differently. So it was just an approximation, and therefore the RFC was updated to requalify it as a proof of concept. And then people were asking, how do we do RAM usage with Go runtime extensions? And so I sketched a little bit inside the text of the RFC, but without making any code changes, how maybe we can do this. And we will come back to this later today. And then someone came up and said, well, what about instead of having your own thing inside the Go runtime, you make the application entirely able to customize the allocator? That is a completely different approach. I suppose that is workable as well. So it is now mentioned in the RFC as one of the possible approaches, even though I think that in the case of the project we were starting with, which is, again, this issue here, custom allocators might be a little bit ambitious. Anyway, so the other things that happen besides the comments on the RFC that are now guiding us towards maybe some additional work. There is a new version of Go that was released. So we have actually Go 1.16, which was released earlier last week sometime. And so the patches we were performing were on Go 1.15 7, and CockroachDB is likely to migrate to 1.16, and so it's pretty important that we continue our changes to Go on the 1.16 branch. We don't want those changes to be too outdated already at the moment we start using them. So that outlines our program for today. So as usual, the link to the RFC is included at the bottom of my screen here. And so what we're going to do now is make a little plan for today's work. All right, so let's go here to do the Go runtime. All right, so we are going to rebase the custom Go changes to the 1.16 branch. Then we're going to process the RFC comments with regards to CPU time and API. So API, we can look at the new metrics package in 1.16 and do the same. And the other thing is CPU time, use real time instead of text. And so this is going to be a support to customize the PR that we started last time. So back then we only had a branch, but in fact I even opened a PR, which was this one. And what we're going to try doing, depending on how much time we have available today, we are going to maybe start experimenting with RAM usage tracking. So there is something we're not doing in this session, but we will need to do eventually, and that is to discuss and reason about the build system. So how to ensure that CRDB continues to work with a plain Go release. If we start adding new APIs in the runtime package, obviously the moment where we start using them in CockroachDB, that will create a hard dependency on those patches. And so we have a legitimate question coming from people, yeah, but it's kind of a big investment to go and rely on the custom Go runtime and so on and so on. Is there a way to make CRDB continue to work without it, even maybe without all the benefits of the custom extensions, like as a way to, to test and maybe get confidence that we didn't break everything with our own custom patches? The answer to this is, yeah, well, that needs to be researched, but at this point, we are still exploring what is possible with custom Go extensions, whereas the build system questions are really more integration, practical, and engineering questions, which are going to cost us some time. It's not trivial, obviously, but does need to happen until we have a strong desire to apply Go runtime extensions in the CockroachDB project. So, if you're a viewer today, if you want more context, you can go to the RFC, linked here, and also at the bottom of the screen, get some readings there, or you can accompany the code changes that I'm performing here. We are also going to start the keyboard thing, so that you can look at the keyboard entry at the same time if you are interested. And off we go. All right, number 1 step. Rebase the custom Go changes to the 1.16 branch. All right. So we have this custom fork of Go, and we have a branch, and that branch was of the 1.16 beta 1, and we are going to rebase this on top of 1.16. Well, rebase or maybe merge. Maybe merging. Let's do the merge. I think. Rebase or merge? Rebase or merge? I don't know. Rebase. I think rebase is going to be nice. Yes, actually, I probably need to list the origin. So, stream. Let's go line. All right. So let's get all those sweet tags from the Go.1.16 branch. So we have a tag and we have a release branch. Maybe we are going to rebase this on the release branch. Let's do this. Like this. All right. So there were a couple of things here. We're going to keep all of them, and then fingers crossed we are not getting any conflict. Yes, there were no conflicts. Success has been achieved. All right. Let's now verify that this builds. I never remember how to build. Maybe build all. Make dot bash, I suppose. No. Build all dot bash? Probably. Right. Let's build this and verify that we don't have any errors with our custom changes. Right. Anyway, so that seems to have succeeded. Also, we probably want to double check our PR from last time. Still works. So that is still this PR. So we are going to, in CockroachDB, need that branch. We need the master branch, in fact, from CockroachDB, and we need our custom branch, and then we're going to rebase one on top of the other. No conflict, fingers crossed. Yep. Okay. Oh, this is it's building too much. This is building much too much. Make that bash. Yeah, that's better. Yeah, it was about to compile all the possible targets and cross targets. That is too much work. All right. So how do we do this? We need to update the go root environment variable, because that is what gives us access to the custom version of the toolchain that we're currently maintaining. Go like this, I think. And then we need to customize path to be go root bin path. And then we'll have go version. Yeah. This properly points to our custom Go version. And now we are going to build CockroachDB with our custom Go toolchain. Fingers crossed, no errors. There were no errors last time, so we are still trying to preserve the same behavior as the previous session. With the new Go version. Exciting. Exciting. The music you're hearing is from the Minecraft beta soundtracks from C418. Absolutely amazing music. I highly recommend. Cool. All right, so the binary builds. The binary builds. Well, sorry, it's not done. We need to actually test it. We are going to start a server. Start single node. All right. And we wanted to have a field. Oops. I need to clear my line of input because I just got myself confused, and I know there is a command to do this. Control C. There you go. Oh no, that's not what I wanted. Node sessions. Thank you very much. There we go. All right, so I have skate-ticks. Still works. All right, skate-ticks. So skate-ticks, now people are telling us it's not the adequate measure of time. So this one works. And now we're going to look at this. So we are going to work on our API for retrieving CPU time. So maybe we are going to look at the real time, and then we're going to tweak the API. All right, so let's go and open this code. Go, src runtime, task group. All right, so for a little context for people who are just joining the stream now and didn't see that last time, what we are doing here is to create a new abstraction inside the Go runtime, inside the Go scheduler, which already has a couple of abstractions. So the Go scheduler has threads that correspond to operating system threads that are more or less mapped to physical CPU cores to the extent defined by the Go maxproc environment variable. And then on top of this abstraction, it defines Go routines, which are called Gs. And the Go routines are a cooperative, well, no, that's not the right word, are a fine-grained unit of concurrency, and they are multiplex over the operating system threads. So the operating system threads are called Ps, and there can be many Gs mapped to a P, and then the Gs also move from one P to another, meaning like a Go routine can be executed by multiple different CPU cores, one after the other. And also Go routines nowadays, since version 1.14, I believe, are preemptively scheduled, meaning that there is a guarantee of fairness of access to CPU time between Go routines. Okay, so that was the executive summary of what Go provides. So it only has Go routines and OS threads, and there is no in between. And so what we are doing in our custom patches here is to introduce a new abstraction in between called a task group. A task group is a unit of abstraction for application level things like queries or sessions in SQL that can own 0 or more Go routines and will have tasks associated to them. And so all the things in the task group are shared across all the Go routines inside the task group. And so what we are going to do is to introduce task groups inside the Go runtime and then associate task groups to SQL sessions or queries. And then this way, all the Go routines that do work on behalf of a SQL session or query will see their resource usage accounted collectively in the task group. So here we are. Last time we prototyped a unit of time called the scheduling tick, with the idea that whenever control is passed from on the processor from one Go routine to another, that increases a scheduling tick counter in the Go routine. In the task group for that Go routine, and that was an approximation of CPU time. Now, since then, folk have come by and said, well, scheduling ticks are not exactly good as a measure of time. They're just a measure of scheduling pressure. And if we really want to do CPU time, we actually want time and not ticks. And so how does this work? Well, we are going to add nanos. And that is cumulative slice of CPU time used. All right. Then we will want an API to retrieve this. So the API we're going to improve later. That's the second item under bullet point 3. Until now, we are just going to have a separate API. All right. And what we are missing here is incrementing the nanos. So this is going to be a little bit tricky to get it right. We need to do two things. We need, first of all, to remember when a Go routine gets scheduled into the current processor, and then when it gets scheduled out, we need to compute this for the task group. So let's do this. The way this happens, so let's move this to a different file. The way this happens is in a separate file called proc, I think. Is it proc or runtime 2? We'll see. So where are the skeptics now? So it's actually runtime 2. Okay, where is this incremented? In the scheduler, maybe? I don't remember, so let's search for it. Skeptics. and it is incremented here. All right. Execute. Okay. Last time g.m p.ptr dot let's get time and then is nano time. Alright. So what we're doing here, we are saying every time a routine comes into a P, like processor, we compute the current time. Then we look at the last time this processor was entered by the previous Go routine, the one that we are scheduling away from. And then we are storing the new current time into that processor. And in between, we are going to add the delta between the new time and the last time into the task group. So this field doesn't exist yet, but we are going to add it. And that is in here. Are these fields by any chance restricted in their order? Yes, there is an alignment thing here, right? Well, that's a different alignment question. Mutex, mutex, mutex. Preempt. This goes there. That's 64. I suppose. Yep. Last scat time is nano time of the last time's Go routine was scheduled into the CSP. Alright, so let's verify what nano time returns. It's an int64. Why is it positive? Why is it signed? That's annoying. Well, if it is signed, we have no choice but to make it sign here too. And then everything is fine here. Also, in our task group, we are going to make this sign too. And then it's going to be int64 here. And now we have nanoseconds. And now we are going to use this inside CockroachDB. And where do we do this? We will have inside CockroachDB in the CRDB internal thing or node session. Where is this being implemented? I don't remember. Con executor maybe? Yeah, I think that sounds right. Serialize. No. Session. Huh. There is a serialize function somewhere. Serialize all. This one here. Serialize. That is where I need. Come on. Where is the serialize method? There is a serialized function somewhere here. There we go. max alloc bytes for the current transaction, and then we have the session here is getDex experimental, and so we are going to have nanos. Nanos. Off we go. And now we're going to try build this because oh no, first of all, we forgot. We need to build the Go runtime with the customization, and then with the Go runtime, we are going to rebuild CockroachDB. So here we have an error. Okay, xIS64 wants a uint64. Ah, I knew this would be an issue. So load 64. All right, so maybe the Go runtime internal APIs have a restriction for they all operate on uint64s, not on int64s. And actually that's good because our unit of times are only monotonically increasing and they are positive. So I will opt to make our task group use unsigned integers here. So that is going to be better. And then that means that in the proc here we need to have nanotime as 64. We are assuming that the nanotime is going to be positive, which I think it is. If it is not, we will have unforeseen problem, but I choose to not be a concern right now. That will need to be looked at later. And then we have an uint64 here. And now we can build this Go runtime. And fingers crossed. uint64 type 64 to xID6. Wait, I don't understand this. How does this work? So xadd 64. Oh, it takes a delta that is signed and adds it to an uint64. Oh well, if it is a delta and it is signed, then in fact I don't really have an issue here. This can be an int64. Then this can also be an int64 that is signed, and that doesn't need to be. And that doesn't need to be, and that should be fine now. Let's try again. Yes, that sounds better. All right, and now we are going to rebuild CockroachDB with this. Yeah. I wonder if there's a way to build the Go runtime without the entire bootstrapping. Maybe I can just have 2 bootstrapping steps for experimentation instead of 3. Or even 1. I know with a C toolchain, for example, I can afford to skip bootstrapping for experimentation. It makes things go a bit faster. I also wish that the build artifacts for CockroachDB were largely preserved from one custom change to the Go runtime to another. Right now it thinks that everything is completely outdated, even though that's not the case. Oh well. Yeah, that might be true. In, let's say, con executor here, I probably need to go to server pb session. Server pb something here. Where is this? In status dot proto session here. Nanos. Right. Cool. Now we can rebuild. All right. Oops. We restart the server. And now we can go SQL. And then... Oh, I am not seeing my node session. My scheduling ticks are not here. Oh, but that's because... okay, so I serialize the value in the session table, but I'm not adding them to the visual table. That is here. Sched ticks. Nanos. The number of CPU nanosecond. All right. And now we are going to add this here. All right. All right. Cool. Nanos. What do we see here? This is a integer. So this is telling us there are microseconds, millisecond, 196 milliseconds. Oh my gosh. This visual table would probably benefit from not being expressed into nanos because that is too much detail. So we are going to say this divided by, so we want a microsecond precision. So 1000, and then it's going to be float 64 divided by 6. And then it's going to be a dfloat and dfloat. And we are going to change the schema here to say double precision, float 8 seconds. Off we go. And we are going to rebuild this. Oh! This is a float. Do we want a float, or do we want even a SQL duration? Durations are... Oh, that is nice. I think that is going to be fine. That might be fine. That is going to be really fine. All right, so how does duration work? Make new integer. I like this. I like this. I like this. So sessions.nanos. And so we don't even have to do our own custom conversion. Cool. Yeah, I suppose that is right. Oh. The type duration does not exist. Yes, it is called interval in SQL, not duration. My bad. better. All right. 700 milliseconds. So if the session is idle, it doesn't do anything. And so the CPU time that is used doesn't increase. And that's exactly the feature we want. We want to measure the CPU time that's currently being used. So here we have barely a second, nothing is happening. If we do select PG sleep of 1 second, for example, that's going to make the session wait for 1 second, but it's not going to increase the CPU time. So we can confirm this by looking at the CPU time both before and after sleep. And we will see that even though the sleep is waiting 1 second, the CPU time used is actually very low because the sleep is idle. And what we see here indeed, there is 1 second and 355 milliseconds to start with, and then 445 milliseconds at the end. And there is no extra second going into the CPU time because of our sleep. If we were to do count star from generate series of 1000, that is actually going to use CPU time, then we will see the value actually increase. So maybe there were too many things here, but as you can see, we started with just 2 seconds in the session, and now we have 20 seconds in the session. So we have achieved success. And so what we're going to do here, we are going to commit our changes, update the RFC, explain to people what's going on, and this way the discussion will be a bit better. All right, so let's start with our Go runtime changes. All right. And then measure actual CPU time in addition to sleep analytics. So we can push this to our branch. Actually, of course, because our branch has been rebased. And now in the CockroachDB PR, we are going to update the PR. Yeah, I suppose. Yep. Save. Commit. Yep. Alright, so the description has not changed. We can push this to GitHub, and that was here. So this does not describe oh, interesting. Someone else has referred to this. Yes, that is correct. And now we're going to update the RFC accordingly. CPU time and utilization. So the previous here had a example. Yeah. In CP struct nanos. Okay. And now we are going to copy paste it's the explanation about usage here, and refer to the PR to say this has been implemented here and there. That is here. And then we are also going to say again, do not include aggregation of CPU time across multiple nodes are distributed. All right. And then we are going to make an example here. So class query. And then we're going to have CPU time. And that needs to be tested in practice with an actual session. All right, so we have here a server that is still running. We are going to start a session here. Then we are going to have another section here. CPU time. How can we make this measurement precise here? I suppose we can't really. So we are going to do our thing here. So PG sleep of 0. So 42 to 71. That is 29. Now, yeah, we probably want to have this as a float because otherwise we can't easily subtract, can we? Or maybe we can actually. Oh, we absolutely could. Anyway, so let's go there. Minus this. Now. That is odd, and that is a problem. That is actually a problem. That is absolutely a problem. Look what just happened. We had a query of a certain number in generate series here, and oh yeah, I know what we did. Actually, okay, so the patch we did is actually broken. Ha ha ha. So look what's happening here. It is as if this generate series here took 20 seconds. Oh my gosh, this cannot be. It is not possible because it was kind of immediate. So we can confirm this and we can say current time. And then if we do current time here, you see the thing appears to have taken 33 seconds, whereas the actual time difference is less than a microsecond. So this time here is bogus, but we can actually figure out why. So actually there is a mistake in the reasoning here, and the original proposal was actually better. We shouldn't have stored last scaled time in the p struct, because if a Go routine moves from one processor to another, we're going to use the wrong field for its duration. The last scaled time actually has to be stored in the G struct, not the p struct. So that was actually an implementation mistake, and we need to fix it. All right, so that is going to be the new so there is a interesting. Okay. So we can't increment the time in the new task group. We have to increment it in the previous task group. So we're going to do so here. Here. And we are going to store in the new GP. All right. That sounds better. And that goes away. And now we are going to move the definition from the field in the P struct into a field in the G struct. And to AP. Now we're going to build this. And we get a seg fault. That is good. That is good. So there is a bug somewhere. We might be switching into the P without a previous go routine. That is valid. Sometimes I have a blank in my head. I'm looking at the code and I don't know what I'm supposed to think, and there is nothing happening in my head and there is some kind of stall. I don't know exactly what's wrong with me. It just happened. My apologies. I use music as a way to kick my brain into activity when it has a stall like this. Alright, we are going to rebuild CockroachDB with our change, which is going to take a little while again, because every time we make a custom build of the Go runtime, we have to rebuild the entirety of CockroachDB. I'm sure there's a way to make this faster. Eventually, if we are successful with all these experiments, we will add unit tests inside our own custom fork of the Go runtime so that we can have its own release cycle separate from that of CockroachDB. But as we are doing those experiments on stream and we want like a bit more tighter development cycles, we are affording to have the test done inside CockroachDB instead, and a bit manual. All this is because we are doing a research project here and we don't actually have a complete roadmap towards solving this in production. Alright, so we are going to start again. Then we have a session here that needs to be restarted. Then this one. A little bit of work. And now we are going to do our things from the RFC again. So what was the RFC telling us? So in the G struct from the current class G in the current G. Okay. And then we had that query to get the data. They seem to be quite idle. That might be okay. I think that might be okay. Let's have them do a little more work. Ah, 0, 0 everywhere. 0 everywhere. That is not great. That is not great. That is absolutely not great. Okay, so maybe our approach here is not working. It's possible. It is absolutely possible. Yet. So okay, so here we consume some time. Okay, that was completely stupid of me. We need to count. Alright. Still have 0 CPU time. Okay. So our approach in here has not succeeded. And the reason is probably that this Kurji, if the previous go routine is not in the GoG field before we get this. And that seems reasonable. And so I think what's happening here, and so I need to go and check the code to verify this, but bear with me. So hypothesis is that when this function executes here, the current G in the processor is not the Go routine we're switching away from, it's actually the runtime system of Go. The actual previous G is somewhere else, and that means that we don't have a previous G pointer to actually work with, and therefore this is always nil, and so this condition is never reached, and so we never increment the value here. So that's what I think is happening here. So what's happening here really is that we lose track of the Go routine we're leaving when we get into a new one on the processor. That is possible and it's okay. We probably want to see if there is inside the P a pointer to the Go routine we are currently leaving. And that might be the M struct. Okay. So it's a scheduling stack, the signal stack. Then we have current running Go routine. Let's see how getG is implemented. To do this, we are going to look at some assembly. And it stops. All right, so there is some special support. All right, so mcall is probably the one I want. So it switches away from the G into the G0 stack. So the scheduler is running on the G0 Go routine. And mcall saves G's current PCSP in gsched, so it can be restored later. All right, that is interesting. So we are going to see where execute is called. All right. Next P alt P. Scheduling, log G. So I think we're making a mistake here. So the problem we are having is that by the time the execute function is called, we may be very far away from the point the previous Go routine has completed its scheduling tick. In other words, we need to catch the executing time at the end of a tick, not at the beginning of the next tick, because in between there might be an arbitrary amount of time spent in the Go scheduler. So, in other words, this little piece of code here, we don't want to have on entry of the Go routine, we want to have on exit of the previous Go routine. All right. So, we have this here. That sounds about right. So ghost get imp is a thing that seems to be called when control is transferred away from a Go routine to the scheduler. And what we see is that the Go routine gets out of the schedule queue. So that would be probably in this area that we are interested to count the time away that the Go routine is leaving. And so we are going to check whether drop G is the thing we need. That sounds about right. So drop G detaches the M and the Go routine M for G. That's good. So if we park the Go routine, we get a suspend. That's a preempt thing. That is for suspending the Go routine during a GC run. Then there is a yield. Yep. And then we have the drop G for go exit when the Go routine terminates. That seems about right. Then we have exit syscall. Yeah, I think we're happy with this. So drop G is a thing that disconnects the Go routine from the current M. So we're going to do our counting of CPU time over here. So that prev G here was garbage because it's too late. And then we are going to have this. And cool. Let's annotate this. That goes away. That goes in. Cool. Cool. Let's see if that builds. Make. seems to build. Now we're going to rebuild CockroachDB with this, and then we're going to test it. Still 0. That is not great news. That is not great news. Oh, I made a mistake. Bad. Underscore G is not the current Go routine. It's current G.m.curg. That is. Ah. I should have paid attention. Okay. Cool. Start the server. Restart SQL session. Restart SQL session. And look at session. And there we go. Ooh, yes. 3 milliseconds. 2 milliseconds. Cool. Here we go. Then we're resuming our experiments here because I think we got it here. And then we're going to do the PG Sleep 0 thing again. If it is 0, it's going to cost us nearly no time at all. That is going to be this one minus this one. And that is something like 900. Oops. What did I do? Microseconds. Oops. Come on. Paste minus paste. It's interesting to see that the other SQL sessions that is no idle. It's not consuming any time. It is idle after all. And it's still 900 milliseconds. Oopsie. And then we do the thing. And that is Is this one? So minus this one. We're expecting something like 10 seconds going on here. Oh, here we go. No. Yeah, we need to, okay, subtract the two values from each other. And that is so great. Cool. Their CPU time. Cool. And we need to explain this in the gstruct with a neat field. Scheduling event. Upon leaving the processor in the drop-g function, we take okay. Upon entering the processor, execute function. All right. And now we have the connection. And now it works. It works. It actually works. It's a nice feeling that it works. Makes me shiver in my shoulders. All right. So we're going to fix this commit. We are going to push it. Hi, rail. Yes, it is nice. It is a very nice feeling. Then we're going to update our PR here. Does that need to be? No, that's the same. We need to update the RFC with this change. Commit. And then push the RFC. The RFC is updated. Then we have this. That is done. And now we're going to look at the next points. So that is going to be our next point. But we've been at this for a little more than an hour, and it's very important when programming to take breaks and move the body and hydrate and so on. And therefore, I suggest we do this, take a few minutes to relax, and then we'll back into it in a few minutes. Maybe something like 10 to the hour or maybe 5 to the hour. Now, enjoy your break, and we will see each other again very soon. All right, we are back on stream. There is a little funny thing that happened. So I was about to take my break and I was like, I really feel like I should be moving my body with Dance Dance Revolution right now. And then part of me was thinking, well, it's probably not exactly good for the audience of the last stream to see me all sweaty and steamy after my break. Why not appreciate it? And I actually did not realize that because of the camera, probably would not notice. Yeah, well, mindset is not the same with remote work, I suppose. So next time, probably we'll take a DDR break without telling anyone. Anyhow, all right. So the next item in today's to-do list is looking at the API for the new GitHub metrics package. We are going to look into this. Oh, look at this. There is a notification in the web browsers as the RC has been looked at. Curious. Blah, blah, blah. Suppose. Yes. 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 Okay, we need to work on the bias. Oh. Profiler labels will be eventually supported by the heap profile. Actually, I don't believe that is true. Interesting. Yes, I think. Cool. All right, we are... Oh, there is even one more comment? No, that's the only thing we have. Okay, cool. Anyway, go metrics. Go metrics, this new package. So this is a new package created defining 1.16 sub-package of the runtime package. And instead, so the idea of this package is that instead of having one accessor method per metric, there is a single accessor method for all the metrics, but which metric is retrieved is specified using a string. And the idea being that each of the metric has a key defined as a string that has a path-like structure with a path to the metric inside the process, like the symbolic, like a symbolic idea of what the metric is about, then followed by a colon, followed by the unit of the metric. And the idea of using strings as opposed to separate methods is that this way across multiple versions of Go it's possible for the runtime to add additional metrics without having to change the APIs that the applications will use. So that's like actually pretty interesting for the project we're working on, since this way we can also consider having metrics for the current task group inside the metrics package without having any additional API. So that's kind of cool. All right, so how does the API work actually? Read populates each value field in a given slice of metric sample. So we need to see what a sample is. It has a name and it has a value. So the name are from the strings above, and the value is the current value of the metric. And here there will be different kinds of metrics, so like basically depending on the type of data, there will be different values, and there will be abstracted away via an interface. Interesting. So I wonder how they implemented this. So let's have a look. Runtime metrics value. Oh, scalar or a pointer. And if you use a float, it does a float 64 from bits. All right. That's pretty trivial. All right, cool. That's easy enough. So this reads the metrics, all the metrics from... Oh, no, okay, like the caller decides which are the metrics they want to read by passing a slice where each of the sample entries has their name fields populated. And the runtime will recognize the name field and then fill in the value corresponding to that name in the array. That makes it possible for the application to choose which metric it consumes. We use have some caveats. Values should not be read or manipulated while a read with that value is outstanding. The data arrays, I suppose. Yeah, so it doesn't lock the struct where the value is written. That's fair. Sample values with names not appearing in all. All, what is all? Oh, so there is the all function. Right, description. The full name of the metric. Alright. So this is like the list of all the metrics available. And we have this. Okay, cool. Well, this API is nice. That makes it possible to read metrics later. However, of course, it's only designed for global metrics that are shared for all the task groups. And if we want to have separate metrics per task groups, that means that it's missing an argument. Given that the path to the metric is a string, we probably do not want to use exactly the same package. So let's see. Is that like a child from a child thing from the runtime read metrics? I like this. So we are going to look at this from that. It's in here. Off we go. Okay, I see this. It is metrics.go, and that uses metric data with global strings, and with a retrieval compute function that does it this way. Okay, that is nice. And then it has a read metrics function. What does this do? It grabs the metrics from initialize the map, and then there is aggregation going on probably. And then it releases the symmetric subsystem. All right, so we can do something like this for task groups, using the same sample struct. So like we have metric value, the kinds, a scalar, and a pointer. Yeah, sure. Let's work with this. Let's work with this task group. So instead of those custom functions, one per metric, we want to have a single function. Read task group metrics. And so we are going to do this. And then it's going to have task group. All right, like this. And now here we are going to do the thing like this. And then for task metrics. Sample.value, finish, and we're done. And then we have here, where is this map define? Init metrics. Once. Once. I wonder. Yeah, so we actually want a once kind of deal with this, but so why is this? Does the metric package does this way? Is because it wants to elide the allocation of this metrics map. If the metric system is not being used, I think that's fine. So we are going to say task group metrics struct that's going to be an int32. And then is there some kind of mutex in the in this here? So what I'm trying to figure out here is if I can use lock inside the I think so, probably not, in fact. Init metrics. Sem acquire 1. I suppose. Yeah, what we don't want actually to... the hell with it. The hell... Oh, but I can't use I cannot use heap allocation in the global scope in the runtime package, because by the time the initializer run, we don't have heap allocator ready yet. Ah. Yeah. Okay, well, this group takes some 32. And what does it have here? Init metrics, metric data in the compute. And here we're going to use something that looks like done. Done. And we need to have a load from the runtime internal atomic empty, and what is it called? We want a load. Go in 32. U in 32. Task group metrics that init done. Once is not 0, then we are done. Otherwise we are going to acquire, say, scheduling. Store. All right. All right. Now we're talking. So task group. And then we're going to have sched. X. And what is a unit? It's unitless, I suppose. X. And it's going to be the code we had here. Come on. Compute. This is out of kind is metric kind UM64. Out of scalar is this. And then there's one. Metrics. So we need to call say thing here. And now we can remove our previous API because it is now substituted. Task group metrics dot metrics. Now that is guaranteed to be here. Compute. And now we can build this. I think. Same acquire needs to be passed through 0 and 0. The following code is morally equivalent to thing.doOnce. Come on. Okay, that succeeded. Once dot sync dot once dot do not initialize. Oh. We will need a description field for all the metrics, and then we need a link. All right, metrics. All right, so there is a go. So task group.go sample here we have a file here. The sample does not change in the runtime. Runtime, that's internal task group. Metrics are read from the curve. Say for the specified task group only. See the documentation. Read. Task group. Cool. Oh, that is not great. I see. We can't depend on the runtime here, I suppose. Interesting. I don't know exactly how to think about this API. Cannot depend on the runtime package. Let's try this. Let's try this. Maybe there will be a circular dependency problem. We'll see. Ah, no, don't complain. I suppose we can do this. Oh. So this builds. Come on. All right. So now I have a metrics function, which means that in my con executor thing here, I'm not going to use runtime this, but I'm going to say metrics. So okay, task group metrics, metric dot. Now I need to have this sample. Sample. And I'm going to have main. And now I'm going to use the strings that we had here. We are going to say metrics.read task group from task group metrics, and we are going to say task group metrics 0.value. uint64. So this actually answers a problem that we knew we had from the RFC, namely what do we do when we are using a Go runtime that doesn't support our extensions? Well, this metrics API makes it possible, because now this API here will be available in Go 1.16 without our extensions, and it will simply return that the metrics are not known. So that we're nearly good with this. The only thing that is not exactly great, which is that the task group abstraction is not present in our in a non-custom Go runtime. So that's going to be kind of a bummer. Anyway, so the Go runtime has built here. We're going to try build cockroachdb with this change. Do we get no error? It's blocked. Suspense forever. So what it's telling us is that our way to initialize here is suspending forever. That is not great. That needs to be fixed. So how is metric sema needs to be set to 1 initially. That explains it. No. 0. Metric sema is 1. There we go. Now we need to build this and build the other thing again. Exciting, exciting, exciting. Start server, start a session, start the thing again, and then do the thing. And here we are. We have some time. Okay, well, that seems to work now. Cool. Let's actually get all the both data to see if we still get our scheduling ticks. That seems right. Off we go. Nice. That succeeded. So we need this, and we need this, and then we need here use an API similar to the new runtime metrics package. here we are going to update our PR accordingly. Stage. Like this. And then we update the RFC to explain what we did. Alright, Trail, you have to drop. Good luck. Thank you very much. And see you next time. Alright. Then we expose the metrics via the new metrics package in runtime metrics task group.go. Oops. Executor. Group. And then metrics.task group. And then group metrics 0.value.64. Cool. Off we go. All right. All right. So the RFC is updated. We are using the new API. That means that we have accomplished this. So let's commit this. Let's commit the other thing. It's already done. The RFC. Cool. What else we have? Start experimenting with RAM usage tracking. No, we are not going to do this today because it is actually quite a larger project and we have a review to go and address in the RFC for today. So I think that it is worthwhile to look at the existing review before going and investigating a new and different project. All right, so, but reviewing the RFC and processing the comment is not actually really a programming activity. We'll need to rephrase the text a little bit. So for live stream, it's not super exciting. I will do that off stream, and that means that for today, we can make a break now It's been already 2 hours, so I suppose quite a significant chunk of time already. And we are going to resume next week with some additional investigation in this area, pending perhaps further comments from the reviewers. Anyway, so that is going to be next time. And to summarize what we did today, we were looking at our C here, this one, and we rebased the work we done last time into the 1.16 branch of Go that was released last week. We verified the change from last time worked. We changed the code, or actually added code, so that we were measuring actual CPU time and not just scheduling ticks. And we changed the API to follow the pattern promoted in the new Go 1.16 runtime metrics. So that was it. That was our changes for today. Thank you for tuning in, and we will see each other next time. Thank you again, and have a good day.